How y'all doing? We're doing question 3 for the project. So we started out with a device that is getting compressed. This consists of a 1 pound mole and 1,000 ranking. It's compressed and loses 3,000 BTU heat into the surroundings. So we actually named the system as the piston and the surroundings as gas 2. And also we're given P1 equals 2.72 ATM, P2 equals 1 ATM from the problem. And the basically the problem is asking if the device exists. So the only way for that to happen is for the entropy of the universe to equal 0. So we're gonna go calculate that.
I'm gonna talk about the assumption that we make, like the system is reversible and the ideal gas and closed system, there is no accumulation and there is no in and out of materials in the system, and it's isothermal, no loss of energy, no shaft torque because there is no machine inside it, and no potential, the difference potential energy because the system is horizontal right here, and there is no kinetic energy because the system doesn't move.
So first we started with the entropy balance of the universe, and we know that this is a closed system and it's reversible, so delta S equals 0. We rewrote the equation so then it's 0 equals delta S of the system plus delta S of the surroundings. Then we did an entropy balance where we canceled out the entropy in and out because there's no flow through the system because it's closed, and there is no entropy generated because it's reversible. And next we assume that there's the mass 1 and mass 2 are the same because it is a closed system and there's no mass being transferred. And this is our simplified equation. And we simplified it further by saying that there's only one gas, so n equals 1, so there is no summation. Next, we simplify the equation by defining delta S hat equals delta S over m. Therefore, the m's cancel, and it's just delta S equals Q reversible over T. And we take the values from the problem statement, 3,000 BTU and 1,000 degrees Rankine, to get us that the delta S of the system equals 3 BTU over degrees Rankine.
At this point, we found the delta S of the system. We now have to find delta S of the surroundings, which is gas 2. To do that, we wrote out the entire energy balance, and since there is no change in kinetic or potential energy, these two terms cancelled out. There's no mass going into the system or coming out of the system, so these two terms also cancel out. And there's no work shaft, so work shaft is cancelled out due to the assumption stated earlier. So our energy balance simplifies to delta M U is equal to work done by expansion contraction plus work done plus heat. And so this goes further to U2 minus U1 is equal to work done by expansion contraction plus heat. To change this into differential form, then du is equal to dw.
To continue the derivation, we want to rewrite du equals dw plus dq in terms of entropy and pressure. So following a derivation on page 162 to 165 of the Thermo book, we arrive at the molar entropy change of an ideal gas, since this is an ideal gas we're working with. We want to switch the value for V, so we apply the ideal gas law, and then we're left with a simplification of the molar entropy change for an ideal gas. Since it's an isothermal system, T2 equals T1, so the first term becomes ln of 1, which is 0, so the first term cancels out. We are then left with plugging in the numbers, and we find that the change in entropy is 1.98. So since this is not equal to 3, as found earlier, this process is not possible, or this device is not possible.